Okay, so I wanted to talk more about proof by cases, and really this comes into play a lot more on the math side and less of the computer science side, but this is something that we are supposed to cover in this class, so we are going to cover proof by cases. This is going to be a pretty mathy video. All right, so stick with me, hang in there, and let's go. So we want to prove that for every integer, if you square that integer, multiply it by 3, and add k, is even. Why do we care about this? Don't worry about it, all right? This is practice. We're in math land now. We're proving things without knowing the use. All right, that's pure math. I'm not actually a pure mathematician, but I'm an applied mathematician, but that's pure math for you. Anyway, how are we going to do this? We're going to do this by cases, because it really depends on a few things. And you might see this and say, oh, let's do it by induction. And while induction does work, apply to problems like this, it's not really going to be useful. We're not really going to be, actually, maybe you can do this by induction. Anyway, we're not going to do it by induction. I kind of want to try now. Maybe after this video, I'll go check it out. But we're going to do it by cases, okay? Because it kind of really depends. Is our integer even or odd? So if k is even, we're going to do some stuff and come to a conclusion. And if k is odd, we're going to do some other stuff and get to a conclusion. We're going to see what happens. So if k is even, then we can write k as 2 times some number. And that number is an integer. All right, that's the definition of an even number. So then, oh my gosh, my cat's going crazy. Then what do we have is, well, then 3k squared plus k. We know k is 2n, so what does that look like? 2n squared plus 2n. Now, it's a good idea. Pause the video, try to simplify this, and see if you can use this to prove that we've got an even number on our hands and not just a really active cat on our hands. Anyway, if you pause the video, hopefully you get this. This is 3 times 4n squared plus 2n. And this is 12n squared plus 2n. Why is this useful? Because we want to prove that we're an even number. How do we prove that we're an even number? If we're double some other number, let's factor out a 2. Now, I don't care what this is, 6n squared plus n. But I'll tell you what, it's some integer. You square an integer, multiply it by 6, still an integer. Add another integer, still an integer. This is an integer, so I've shown that our number is 2 times some integer. Okay. So that means that 3k squared plus k is even. We're halfway done. Right? Because that was just for one case. But we have to exhaust every possible case. Luckily here, there's only 2 cases, right? Either k is even or k is odd. Well, what happens if k is odd? Hopefully the same thing. All right, well, if k is odd, then similarly, right, we can write k as 2n plus 1 for some integer n. Well, then what do we have? We have 3k squared plus k, right? Yeah. 3k squared plus k, and we're going to hope that this is now still an even number. We want to show it's even regardless of what k was. But now k is 2n plus 1. Oh, yeah. We get to do some foiling. When you do that, you're going to get 4n squared plus 4n plus 1. This is just 2n plus 1. We don't need those parentheses. Let's distribute and get 12n squared plus 12n plus 3 plus 2n plus 1. Let's combine like terms. Right? I'm sure you love all this stuff. We get 12n squared plus 14n plus 4. Why does this matter? We're trying to show we have an even number. Well, we can factor out a 2. And if you factor out a 2, you're going to notice, just like before, what's left over is still some integer. We have double an integer. That means we're an even number. So regardless of whether k was even, in which case this was even, or k was odd, it was still even. It's even. So whether k was even or odd, 3k squared plus k is even, and that's how you do proof by cases. It's saying, I don't know how to prove this for any situation because it really kind of depends. Well, either it's A, B, or C, or D. Let's just check what happens for each of those cases. And if they all match, then it didn't matter what it was, and we're good to go. So it basically just breaks the proof into subproofs. And as long as your subproofs form some kind of partition, then using like that, set theory logic terminology we talked about before, then you're good to go. So what if we have more than 2 cases? Let's do another very exciting, very interesting problem. Let's say I want to prove that for any natural number, 2n squared plus n plus 1 is not divisible by 3. Why do I care about that? Who knows? Ask the pure mathematician. We're going to prove it. And here it's not going to matter whether n is even or odd. Here it's going to matter how is n divisible by 3? And if not, how? So specifically, know that, every number, if you divide it by 3, pick any integer and divide it by 3, you'll either have a remainder of 0, 1, or 2. If your remainder is 0, then of course you were divisible by 3. There was no remainder. But if you have a remainder of 1 or 2, then we weren't divisible by 3. And it's going to matter, this is a lot easier to answer, whether we know whether n was divisible by 3 or not, and specifically how, what the remainder is. So here we go. Case 1, n is divisible by 3. Again, another way of saying that is the remainder is 0. Well, if that's the case, then n can be written as 3 times some k, for some integer k. There exists a k in z. We could use that knowledge as well, right? That information. So n is going to be 3 times k if it has a remainder of 0. And if that's the case, you're going to see something, we're doing something very similar here, but not quite the same. Because we're not trying to show it is divisible by 3. We're going to try to show that this isn't divisible by 3. So what do we have? N is 3k squared plus 3k plus 1. Let's simplify. That's 9k squared, so 18k squared plus 3k plus 1. And of course, we can't factor out a 3 here. If we could factor out a 3, then this would be divisible by 3. But watch this. Let's factor out a 3 from the first 2 parts. Why is this useful? Because that shows that this is divisible by 3. And any number you pick that's divisible by 3, if you add 1 to it, you are not divisible by 3 anymore, right? 3, 6, 9, 12, 15. All these numbers that are divisible by 3, you add 1, you get 4, 7, 10, 13. Of course, they're not going to be divisible by 3 anymore. They're going to have a remainder of 1. So if n is divisible by 3, this thing actually has a remainder of 1. It's certainly not divisible by 3. All right, so this right here is divisible by 3. So conclusion is we're not divisible by 3. I don't like using exclamation marks. They look like factorials. And now we'll look at the other cases. Okay, so case 2. Should really do this on the next page. n divided by 3 has a remainder of 1. So what's that going to look like? That means that n will be 3 times some integer plus 1. It'll actually kind of look like this. I highly recommend you pause the video, try to finish out this proof in case 2 and case 3. It's not probably very illuminating if you just watch me do this problem. It's much more useful if you pause it and do the problem, and then you can just fast forward and check to see like what happened. All right. So if n is that, we have 2 times 3k plus 1 squared plus 3k plus 1 plus 1. It's going to be a little bit of a headache. This is 9k squared plus 6k plus 1 plus 3k plus 2. I'm going to go through this fast because I'm assuming you've already done it. You're being good students. All right, we have 18k squared plus 12k plus 2 plus 3k plus 2. And just like before, we'll combine like terms. K squared plus 15k plus 4. And we're going to do the same idea as before. We want to say, oh, here's a part that's divisible by 3. And then let's add something so it's not divisible by 3 anymore. So actually, instead of combining like terms into a 4, notice the other parts are divisible by 3. Let's split this up into 2 things. Let's split it up into a 3 and a 1. Why would we do that? Because we can factor out a 3 from the first part. 6k squared plus 5k plus 1 plus 1. And now we're in the exact same situation where this whole thing is divisible by 3. If you have a number that's divisible by 3 and you add 1, you ain't divisible by 3 anymore. So just like before, we're not divisible by 3. But unlike the last example, we're not done, right? n divided by 3 could also have a remainder of 2. So let's look at now there's more than 2 cases. That's going to be n divided by 3 has a remainder of 2. So that means that n is 3k plus 2. And it's going to look very, very similar to what we had before. 2n squared plus n plus 1. It's going to be almost the exact same strategy. I'm not even going to do it. Okay? You're just going to go through the steps, it equals, and you're going to get something that's divisible by 3 plus 1, maybe plus 2. I don't remember off the top of my head. And then you're going to get, okay, not divisible by 3. So you're going to say, well, it didn't matter whether n was divisible by 3 and had a remainder of 0, whether n had a remainder of 1, whether n divided by 3 had a remainder of 2. It didn't matter. Either way, 2n squared plus n plus 1 was not divisible by 3. So it's another way of breaking things up into smaller subproblems. Induction, right, is always using the previous one to prove the next. That's the kind of subproblem induction breaks things up into. Cases breaks things up into a different subset, a different partition, if you will. But anyway, for all n greater than or equal to 1, 2n squared plus n plus 1 is not divisible by 3. We looked at every single way that n could exist, and we showed that the result was a number that wasn't divisible by 3. And that's how you do it. So that's pretty much what cases look like. And again, you saw in the first strong form induction that we did induction and had cases inside of induction. And that's how a lot of these proofs are going to end up happening, is you'll do one proving method, and then you're going to have to show something within that, and that might use a different proving method. And again, you're just building and building and building things off of the backs of other things that you've built, right? Like building a house or something like that. Okay. That's pretty much it. That's proofs. That's the end of the chapter. That's the end of the class. Oh man, shed a tear. But again, one of the things I really like about proofs is that it really is about like solving. It's like we have all these tools. How can we arrange the tools to make a logical argument that's airtight and stuff like that? I think it's a fun little logic puzzle. It's kind of the same reason I like coding, and also like coding. Like there's a really nice way. There's elegant ways of doing proofs, and then there's also non-elegant ways of doing proofs that still work. Right? And we've all been there. Sometimes we write a code and say, man, this is some nice code, right? It's very clean, very straightforward. I'm not wasting a lot of steps. People can read it. And then sometimes it's, especially I know a lot of my friends who are programmers, right? Sometimes you just need to get the assignment done. Sometimes the boss asks you to program something and you do it, but you look at that code and you say, I sure hope we don't have to look at this in the future. All right. And that's kind of similar to proofs, which is pretty cool. I enjoy it. The fact of the matter is most computer scientists aren't going to do that much with proofs, but the logical structure is good to know. The logical structure is good to practice. And of course, you're going to oftentimes be using things that are proved by other people. And if you're a theoretical computer scientist, then yes, you are going to prove these things. Proving things in terms of like algorithms, proving like whether algorithms will always work, proving if you're really interested in something, it's one thing that hasn't been proven but has been conjectured, or some people think it's true, some people don't think it's true. It's kind of a fun little debate, is like the difference between I believe NP hard problems and P hard problems. It's pretty interesting as well, but I'm not going to go into that, and honestly don't remember enough off the top of my head to really say more, but there's some really cool stuff with proofs. Anyway, have a good one. Goodbye.